the coordinate representation because this connects to the classical interpretation of the L and all those operators. Okay, so the route that we have taken so far is considering how a system rotates and then deducing what is the Hermitian operator that generates rotation, and then deducing the commutation relations of generators of rotation in different directions, and then deriving everything about angular momentum based on this route. Well, in the middle, we checked that actually we found LZ, the operator, was xpy minus ypx. So it actually agrees with the classical mechanical analog of angular momentum, right? Okay. So now let's go a different route. Let's start from classical mechanics and then check the consistency of what we have done so far. So what I mean is, let's start with this. Okay. So the vector operator of angular momentum is given by the cross product, and these are all vector operators. We start from here, and then we find the, in spherical coordinates, the explicit coordinate representations of these operators, and let's check if they're Hermitian. Okay. So now what is P? Okay. P is H bar over I del. And this del should be interpreted as the, there are several possibilities for del, right? It can be divergence, it can be gradient. Which one should this be? Gradient, right? Because our wave functions are scalars. So the gradient, what's the gradient in spherical coordinates? It's like dr plus 1 over r d plus 1 over r sine. Right? Now the way you remember this is, first of all, their dimension must match. Right? If you're taking derivative with respect to an angle is dimensionless. Right? So these things lack a dimension of 1 over r. So you attach these terms. And then the sine theta term has to do with, just remember it, has to do with I don't want to explain that. So this is what it is in spherical coordinates. Right? So now let's take, say, Lx. Okay. So let's take x hat dotted with this. So unfortunately now we have to make use of some very confusing notation. This is the, let me use something else. So let me use x to be E1. Okay. E1. And this E1 vector is the direction vector in the x direction. Right? So x, y, z is 1, 2, 3. That's their labels. And the e's are the orthogonal eigenbases. Okay. So now, what is this? This is E1 dotted with. And if we take R cross with, oh sorry, I forgot to attach the unit vectors here. And remember, these hats are unit vectors. These are not the operators. Okay. So unfortunately, we have to run into this difficulty. So let me write this as R hat cross H bar over I the R hat.
It's important to put the unit vector to the left of the operator. In the previous line,
yeah,
it's important to put the unit vector to the left
of
the operator because they don't commute.
Right, they don't commute. Yeah. My bad. Remember, in spherical coordinates, right, the direction of the unit vectors are position dependent. now if we do this cross product, well, the R term goes away, right? Because R hat cross R hat is nothing. Okay, so R cross theta gives you phi, right? And then R times the 1 over R, that just gives you 1. So this is E1 dotted with H bar over I. Okay. So R cross theta is phi. And then it's just dd theta. That's one term. And then plus R cross phi is minus theta. Right? So I should have written the minus. And then R cancels with this R, you get a sine theta left over. So it's minus theta hat 1 over sine theta d phi. Correct? So now we want to pick out this E1. Okay, so the way to do this is write E1 in terms of R theta phi. Okay. So if you remember, now let's do this in our head. Okay, so what is x hat? So x hat is E1 in this case, and is represented by the R theta phi as R sine theta cosine phi, plus what else? Theta sine theta sine phi, right?
Yes.
Yeah. And then it's plus what? Phi cosine theta.
You should swap the position of theta and phi.
Swap.
No, like phi sine theta cosine sine phi. Theta cosine theta.
Oh, okay. Yeah.
So,
Let me cheat. Let me copy those over here. Oh yeah, that's right. So we got one of them, right? Theta has cosine, theta cosine phi. Okay. Minus sine phi hat. So this is the expression. And you can always get this expression by drawing a little diagram. So it's not that extremely important. Okay, so now let's compute this dot product. Okay. So there's no R hat term. Okay. For the theta component, we pick out this, right? So we get for the theta component, now this E1 dotted with this is equal to H bar over I. Okay. The theta component, you have a cosine theta divided by sine theta, and that gives you a cotangent, right? Correct? Yeah, cotangent. So it's minus 1 over cotangent theta. Okay. And then it's cosine phi d phi. Correct? And then over here, this is simple. This is just, for the phi hat, this is just minus sine phi d theta. And so now you notice something interesting. In classical mechanics, I'm free to compute what? I can either do L dot E1 or E1 dot L. Right? But in quantum mechanics, because things don't commute, we can actually only do it in the correct order, this way. Okay. Right, so this is Lx, right? The operator Lx represented in a spherical coordinate. Okay. Let's not work with Lx because Lx is quite complicated. Oh, sorry, this is not 1 over cotangent theta. This is just cotangent. Okay. Let's work with Lz. Now if I were to compute this dot product, I'm only going to pick out the this component, right, the theta component. And the theta component minus sine theta divided by 1 over sine theta, this just gives you d phi. Okay. So we get that the LZ, the coordinate representation of LZ is just 1 over h bar d phi, right? So this actually agrees somewhat, without the h bar thing. This agrees with what we did for the when we explicitly solved the Schrodinger equation by separation of variables. Remember, we arrived at the eigenvalue problem for the z direction, for the phi direction was d phi squared big C is equal to minus m squared big C. But now because of quantization, we have introduced this h bar. So now let's do a consistency check. By using this classical mechanics analogy, okay, so you can think about this very easily. This computes the rate of change in the phi direction. The rate of change in the phi direction describes a rotation in this direction, right? So by using this classical mechanics analogy, let's check if the LZ produced this way is actually Hermitian. Okay. How do we check it if it's Hermitian? It has some eigenfunctions. I'm going to write as phi. Okay. Alright. And we know that the eigenfunctions they are going to look like something like e to the I m phi, right? Something like this. Okay. And then any linear superposition of this is phi. Right? And to have LZ be Hermitian, what do we require of the eigenvalue? The eigenvalue must be real. So right now, without any other condition, we deduce that, well, we have a class of eigenfunction that looks like this, and all we require is that m be a real value, right? Okay. So now let's try to impose the condition of requiring LZ to be Hermitian, and see what kind of a spectrum, what kind of a restriction do we place on the eigenvalues. We would hope that we get that the eigenvalues are either half integers or integers, right? Yeah, let's see if it comes out. All right. So, how do we do this? Well, to check that it's Hermitian, we would like to find if phi1 conjugate. Okay. Well, h bar over I phi2, and the integral is from 0 to 2 pi, right? Okay. We would like to see if this is equal to this conjugate, correct? Right. This is the definition of Hermitism. Okay. So how do we do this? Well, we again do integration by parts. So this one gives you, you're going to get phi1 conjugate phi2. Of course, you're going to get h bar over I times here. And then this is evaluated at 0 and 2 pi. Okay. Minus h bar over I. And then from 0 to 2 pi. Phi2 be phi1 right? Okay. So now if I put this in and take out a conjugate, this gives me this term. So no problem. The requirement of it being Hermitian is just we require this term to go to 0. Okay. So now let's study what does that tell us. So the h bar over I term doesn't matter. Okay. So I just want phi1 conjugate evaluated at 2 pi times phi2 2 pi minus phi1 conjugate at 0 phi2 at 0 to be 0. Okay. So now, obviously, the sufficient condition would be for these things to be the phi 1 and phi 2 to be periodic with period of 2 pi. Then this is trivially satisfied. Okay? But that's not the necessary condition. To deduce the necessary condition, okay, what we will do is, since so far we have only been able to restrict this to real values. Okay? So let's do a Fourier transform kind of thing. Let's expand this as going from minus infinity to infinity, dn, or I should say dm, okay? And e to the I m3, and then let's use big M 1, and then it's what? M1. Let's expand this with respect to M1. Okay, is that okay? And then the other thing we expand with respect to M2. Okay, so now let's go ahead and plug these in. Okay. So for the first term, what are we going to get? We get M1 conjugate M1. And then it's, because we have conjugated this one, e to the minus I m1 phi. And the phi is at 2 pi for the first term. Okay. And then the second one is e to the I m2 phi. M2. And the integral is over minus infinity. dm1 dm2, right? Right. This is the first term. And then the second term, everything is 0, right? So we just plug in the values at 0. Okay, so we forget about the phase factors. M1 conjugate M2. And this must be 0. Right? Okay. So now these two integrals can actually be combined. So finally we get this integral must be vanishing.
Shouldn't M2 phi also be M2 2 pi? In the first
Oh, I
step.
forgot. Okay, so we get the common factor is M1 conjugate M2. And then you're multiplying by what? E to the I m2 minus m1 times 2 pi minus 1. This must be 0. So now, since we started with two arbitrary eigenfunctions, phi 1 and phi 2 are arbitrary. Right? These two are also arbitrary. Right? So we get this difference multiplying by an arbitrary function is 0. And we must get this is 0, correct? Okay. So if this is 0, what does it say? E to the I m2 minus m1 2 pi is equal to 1. And so once again we get that m2 and m1 are separated by integer values. Alright? So they're either so right now, by saying that they're separated by integer values, that doesn't say that they're either integers or half integers. To say that again, we need to impose the symmetry condition of up positive z direction and negative z direction, right? Okay, so we get the same kind of eigenspectrum by writing out from classical mechanics, writing out the explicit representation in the coordinate basis, and then requiring it to be Hermitian. So going either way is fine, and our results are completely consistent. Okay. So now I think this is all we need to talk about for angular momentum. Let's move on to spin. Okay. Are there any questions? No. All right. So let's talk about spin. So first of all, let me give you an illustration of where the spin come from. So for that, let's think about, well, so far we have been talking about the rotation of a scalar field in xy plane, or about the z-axis. So, and the rotation of a scalar field is modeled by the operator LZ. It's generated by LZ. Now let's consider the rotation of a vector field. Okay. So remember before we drew this diagram, right? X direction, Y direction, and then we did some kind of rotation with respect to by an angle phi. Okay. And then we say, okay, the value at phi x prime y prime will be replaced by the value at phi x y. So if you remember the rule here, for scalar field, the rotation rule is, okay, phi of x prime y prime is equal to phi x plus y epsilon y minus. Right, let me check it. Yeah, correct? Okay. This is what we derived in the previous lecture. And now let me label epsilon with epsilon z, so that we indicate we're rotating about the z-axis. And in this picture, okay, this would be epsilon z. Okay. Remember, if you think about how the position eigentests are rotated, it will be the opposite of this. But the rotation for a field is that of a replacement, right? So it goes the other way as how the eigenbases are changing. Okay. So now let's think about a vector field. Okay. For a vector field, maybe we have two components. And let's say that before the rotation, to make things simple, we say that one component is in the x direction, one component is in the y direction. Okay, and let's call this phi of x. This is psi of y, okay. And it's associated with this point. So this is the situation before the rotation. Okay. Now after rotation, we get. Let me draw a very exaggerated rotation. So maybe it's rotated here. The rotation should preserve this angle, right? Because we're rotating the whole thing with respect to this z-axis. This is x, this is y. Okay, so trying to preserve that angle, we get the x component, psi x is here, okay, and then psi y is here. And this angle is some phi. Okay? So the rotation of a vector field is more complicated because, as you see, not only do I do replacement of the values, I also mix the x component and the y component there. Because now, if I try to project this new vector field at this rotated location onto the x and y axes, I get that. Right, this is the x-axis. This is the y-axis. Their components are mixed, right? So to rotate a vector field, I need to first do the replacement as treating them as two separate scalar fields, and then do the mixing of the components. Right? So now, let's carry this out. So the first step is to do the replacement as if there were two independent scalar fields. Right? So phi of x. Okay, x prime, y prime goes into phi x of x Correct? Okay. And the same thing, the same kind of replacement rule exists for psi y, because we're treating them as two independent scalar fields. Correct? Okay. Then the second step is to mix their components. Right? So now think about an infinitesimal rotation. Right? So obviously from this picture here, if you can see it, okay, the phi x is going to contribute after the rotation to the y direction by an amount of sine theta phi. Right? Correct. This is also phi here. Okay. So then we mix the components and we get phi x, x prime, y prime, phi y, y prime. Well, we say that the x component is going to contribute to the y component by a factor of sine phi. And in infinitesimal rotation, sine phi is given by just phi, right? So we use epsilon z to denote that. And this is epsilon z phi as psi of x given at this replaced position as phi epsilon z phi minus. Okay, and then also the original rotated one. Okay, this is it. And then you see that the y is going to contribute to the minus x direction by an amount of sine phi as well. Okay? So you need a minus epsilon z sine y. Okay? Okay, so this is sine x rotated as a scalar field minus sine y rotated as a scalar field. Okay, so you see that this is the result of our infinitesimal rotation on a vector field with two components. So this is more complicated than rotating a scalar field in which we just do the replacement. Okay, so now if we write this out in terms of matrices, okay, we can say that, well, what does the job of replacing the components, replacing the index? This was derived in the previous lecture, and the angular momentum operator LZ does this job of replacing the. Remember, if we Taylor expanded this, you get y ddx and x ddy, right? So that is done by LZ. So now I can write psi x, psi y. After the rotation, let me write them with prime to indicate after the rotation. Okay. This is equal to, well, some matrix. Since this is a infinitesimal rotation, we know that we're going to get the identity matrix, right? Being the leading order term. Okay. And then from the previous lecture, we derived this. Putting LZ in the diagonal elements. Because why do we put them in the diagonal elements? Right? Because although LZ causes a replacement of the index, it doesn't mix the two components, right? Yeah. So the scalar field psi x is going to go to the rotated psi x prime, and so forth for the psi y component. So we know that the action of LZ is on the diagonal elements. But for the other action is on the off-diagonal elements because it's the mixing of the two components, right? And let's look at what the other action is. The other action is I have a minus epsilon adding to the psi x component, right? So this, if I take out a minus I epsilon z, okay, then I will get a 1 here, right? Oh, it must be some h bar. I will get the h bar here, right? Yeah. And then over here, I have an epsilon adding to the y component, right? And since I've taken out a minus I epsilon, I get a minus I h bar, right? So we get an off-diagonal matrix that completes that does the job of rotating, mixing the components. Right? Right, so for a scalar field, it's very simple. You just have this LZ operation. Right? But for a vector field, you get something else. And this thing we call spin. Okay? So to rotate a vector field, we don't just get LZ. We get LZ plus some rotation of the components. And we can call this J. This operator J. So actually, if the wave function has more than one component, then you'll see that intrinsically it's going to have something called the spin under rotation, right? To generate a rotation, a full rotation of a vector field, you need something more than the angular momentum, and that part we call the spin. Right. Now this is saying that if I had a vector field that was originally in the x and y direction, but this does not necessarily have anything to do with the electron or anything, right? We're just telling you that the reason that the electron has spin is because intrinsically the electron has a two-component wave function. And one component we call it spin up, one component we call it spin down. I'm not saying that one component is in the x direction or one component is in the y direction. Because if you look at this, okay, then you derive that, well, this must be the matrix for rotation in the z direction. So you will call this as z. But then you will be wrong about the electron. This is just an example of a vector field, but this has nothing to do with the field of the electron. The field of the electron, if you want to write it out this way, is quite complicated, and it's not part of quantum mechanics. Okay. In quantum mechanics, well, based on this observation, all we say is that, well, since the electron has intrinsic spin, it must be that its wave function is a vector wave function. It has two components, because we know that, well, the number of components here actually just gives the number of possible spin values you can have. Okay. So for electron, since from experiment we find that, and this is extremely important, is that for ordinary quantum mechanics, you can only input this information from experiment. From experiment, we find that regardless of whichever direction, if I measure the spin of the electron, I'm going to get plus minus 1/2 h bar. Okay. I'm going to get this. Two things are not possible to derive for us. First of all is why the electron has a non-integer spin. Because over here, although I said there's something extra, I'm not saying that these spin must have non-integer eigenvalues. Right? I'm just saying the spin acts like a special kind of angular momentum. Okay. One thing we would not be able to get is why the electron has 1/2 spin from our theory. Okay, but this is easily an input from the experiment. Another thing is why the electron can only have two possible spins. But these are all inputted from the experiment and we accept them. Okay. So since the electron from experiment can only have these two, we know that the electron has a two-component wave function. And we call the one component, we call it the spin up. Okay. So to denote the electron, we sometimes write this. Right? The psi is the spatial wave function, okay, with a upspin, and then the spatial wave function with a downspin. Okay, so now we call this two-component wave function of the electron a spinner. Okay. In many applications, because the spin is an intrinsic thing, it's a degree of freedom for the electron. So in many experiments, we can actually study this degree of freedom by itself. Okay. And when we study this degree of freedom by itself, everything is extremely simple because we can forget about this spatial wave function. Okay. Because that's irrelevant to the experiment. And we only consider the spin degree of freedom, then everything is just in terms of two-component vectors. So let's say that we diagonalize this, let's say that we choose the z direction to be special. Okay? So we have a spin up in the z direction, and we call this, so the up spin state is going to be labeled by 1, 0, and the down spin state is going to be labeled by 0, 1. And I'm saying that these are the eigenstates of the spin z direction. Okay. So now in this eigenbasis, we can write down the matrix representation of the spin operator, right? So since SC when operated on this 1, 0 thing, which is the spin up, it's going to give me a spin up value, which is h bar over 2, right? Now S3 operating on this 0, 1, this is going to give me a minus h bar over 2. So I deduce that, well, the matrix representation of S3 is, take out the h bar over 2, 1 minus 1, 0, 0. Okay. And why do we require the off-diagonal elements to be 0? Because these two are orthogonal. So this is 1, right? And then now let's think about the raising and lowering operators we just derived, right? So we can have S plus, which is Sx plus I Sy. Now what is the action of S plus? If it acts on the down spin, it's going to raise it to the up spin. If it acts on the up spin, it's going to be 0, right? So we get S plus, okay, 1, 0, and this is 0. And then S